In this module, we are going to learn about Newton's first law of motion. And there is a big chance you would have heard of this law. This law goes something like this, that every body will continue to remain at the state of rest or motion with constant speed in a straight line. In the absence of a net external force. So I think you would be one of two kinds of people. One who would be like, what is this? What is this? This is like a mouthful. So many words written here. My God. And another like, yeah, I've already heard this, and yeah, I remember all this. So what I want to tell you is, both of you are in for a surprise. Okay, whichever category you fall in for. Okay. First thing is, let us understand the importance of all these words over here. All English words I understand, okay, but what do I mean by this net, this external force, constant speed in a straight line and all? Okay, so if you saw the last module, if you have not, I suggest go and see that. I had promised you one thing, that everything that's there to be learnt about dynamics can come from this one equation, and that equation was F equal to ma. Okay, and in this F, the F is what stands for this net external force. Okay, F stands for this net external force. Okay, and according to this definition, what is said about the net external force? There is an absence of it. Okay, what do I mean by an absence mathematically? That this F is nothing but 0. Okay, and this equation tells me that if F equal to 0, what can I say about acceleration? Yes, the mass is not 0, it's not a massless body, I'm assuming. Then the acceleration has to go to 0. I should be ideally putting vectors over here, because if you remember, force and acceleration are vectors, and these being 0 means they have no direction and they have no magnitude. Okay, and yeah, you've studied acceleration, right? If acceleration is 0, what can I say about the velocity? Does it have to be 0? Does the velocity have to be 0? Think about it for a second. No, right? Because acceleration is equal to dv by dt, and if this is 0, what I can say is the velocity is a constant. Yeah, if the velocity is constant, what can I say? That the motion has to be with a constant speed in a straight line. Okay, or it could be at rest, right? So yeah, I hope you like this. So this whole sentence can be deduced from just this small equation and a special case of it when the force is 0. Okay, so let me clear the equation out for you. Now that we understood the origin of this first law, let's try to understand a little bit more about this. Okay, first thing, let's give history its credit. This is not really Newton's first law. This is due to our friend Galileo. Okay, so Galileo is the one who first came up with this idea. And yeah, you have studied this, and I had also studied this much earlier in life, and I used to think I'm very smart now. I've learned a lot of physics, and you know what? Then I went to my 5-year-old brother at that time, and I told him this. I told him exactly what this law says. Okay, I told him, I thought it was very common sense. What is there big in this law? Okay, it's a very simple law. It says that if there is no external force, if there is no one pushing, then the body can be at rest. This makes sense. This makes sense to me. This makes me happy, yeah. Or it can be in motion with constant speed in a straight line. I thought it was common sense. Then I went and told my brother that, hey, if you were there again with a smiley face, not really, little sad it came out. Okay, and you kick a football. This football can keep on moving forever and ever. This is what it says, right? It can keep on moving in a straight line forever and ever. But he was like, hey, what are you saying? Just because you gave me one ice cream, will I believe anything? Yeah, it's like, then it struck me that this is not at all commonsensical. Okay, and history is pretty much a witness to this, because human beings have been around for more than 150,000 years, and we built the pyramids and we did so many things, and we did not know this basic law of nature. Okay, and there was a time when Aristotle, who was a philosopher, and at that time philosophers doubled up as scientists, he said that rest is the natural state of all objects. Rest is the natural state of all objects. And we believed him. We believed him. Why? Because this sentence that right now is not common sense, right? We, in the real world, what do we experience? Not the real world, in the immediate world that we see around us, what do we experience? That if you kick a football, it comes to rest after some time. We don't see ever anything going with constant speed in a straight line without any external agency. Okay, so that's why people believe in Aristotle. And this myth continued for a long time till about the 1600s. At that time, Galileo brought this brilliant first revelation that we had in the study of mechanics, the study of dynamics, and he said no. He said no. Why should I believe you? Just because in the world around me this doesn't seem to happen commonly, how can I be sure that rest is the natural state of all objects? Okay, and what he did, and somewhere the answer to why we got fooled for such a long time. Okay, what he did was he conducted a thought experiment. He just thought. There was no way he could do this experiment. He was conducting the world's first thought experiment, and the first thought experiment of the world was this. What he thought is, if I have two inclined planes, this inclined plane 1 and inclined plane 2 like this. Okay, let's look at the first case now. Yeah, shut your eyes to the ones below. So, if there is a ball, it's rolling down this inclined plane, and if there is another inclined plane with a higher angle, this theta 2 and this is theta 1, and this theta 2 is greater than theta 1. Okay, then he saw that the height that is climbed has to be the same in both these inclined planes 1 and 2. What does that mean? That means that the distance covered, this distance, is actually lesser in the inclined plane 2 than in inclined plane 1. Okay, then he thought, let's assume this I saw in a real inclined plane. Now let's think about a inclined plane which is completely smooth. Okay, which is completely smooth, which is frictionless, and then let's start to decrease this angle. So now you see this theta 2 is lesser than theta 1. You played with it. Okay, you played with it and you reduced the angle, you being Galileo. Okay, so he reduced this angle and he saw that a larger distance is actually being covered in inclined plane 2. Interesting. Then he thought, what if we extend this and make theta 2 0? If theta 2 is 0 degrees, how much distance should the ball cover in this not inclined now, just plane 2, when it comes from inclined plane 1? Okay, the answer is that this has to catch up to the height that it came from, to h. And can it ever catch up? Yeah. Think about it for a second. This is a perfectly smooth, this is like more smooth than ice, and the bald head of your, favorite WWF wrestler or anything. Yeah, this will not ever come to rest, will it? Will it ever come to rest? Think about it. The answer is no, most probably no, because this is a thought experiment. Okay, and I'm sure you would have understood till now. We were fooled, your young brother also was fooled, and you also, I don't know if you've thought about it, are actually fooled in real life and think that this is only a part of the textbook. Okay, this constant speed thing, because everywhere around us, when I kick a football, it goes through air. There is the force of gravity pulling it down. There is this whole earth over here which is pulling it down. Okay, there is air resistance. The air is pulling it back. If I push something on the ground, the ground is exerting some friction force on it. That's stopping it. So the net external force is not zero. This is not zero. Okay, it is causing retardation, because F equal to ma means that if the force is opposing the velocity, then the acceleration will also oppose it, and the body will come to rest. And this is why we were proven to be mistaken in our understanding of motion for such a long time. Okay, and this tells us something very interesting about science, why we need science, because our intuition, our common sense can prove to be wrong a lot of time. So we should keep questioning it. Okay, now coming back to this, a lot of times people ask, okay, your friend might ask you, how can you prove this Newton's first law? This is very interesting. I want to take this opportunity to tell you something about laws in physics. Laws cannot be proven. Okay, a law can only be verified. I'll tell you the difference. The difference is, when I say that the body will continue to be remaining at rest or at constant uniform velocity motion forever and ever, how are you ever going to verify this? You will have to look at the body forever, which is not possible. So then some curious one among you might ask that, why should I believe this law then? It's a very fair question to ask. The answer again to this is because it's not been disproven till now. Okay, in other words, if you go to some place which does not have friction, for example, if tomorrow you become an astronaut, this time you're happy. Okay, you're not sarcastically happy, this is just like I'm bad at drawing. Okay, and you're somewhere away from Earth, and you throw a ball. Like, you're really away from Earth and everywhere else where the gravitational force is very negligible from all of them, all of the planets and everything. I'll tell you in detail about gravitational force, but you have some common sense intuition about it. Okay, so if you throw this ball, this will keep on, once you are done with exerting a force on it, if you give it some initial velocity, it will keep on going till you observe it in a straight line along this same path. Okay, and that's why we believe in Newton's first law. Okay, wrong, my bad. Galileo's first law of motion. Okay, so, and thank you for watching this, and I hope you enjoyed this as much as I did in making it. And please subscribe the channel, and so that you can dive into the next video where we'll deep dive into this first law of motion, what its implications are, and also is it always valid.